Excellent.
Okay, so for our last speaker of this session, we have David Peinador Veiga, also from Queen Mary, who's going to tell us about classical solutions and their double copy from Amplitudes.
Yeah. So thank you, Julio, and also thank you for well, to the rest of the organizers for giving me the opportunity to talk to all of you about this work I've done in these two papers. In the first one with Ricardo, Donald, and Matteo, and also Silvia joined us for the second paper, this one which actually appeared only yesterday on the archive. So as many of you might know, there are several structures in exact classical solutions in both well, GR and electromagnetism that resemble the BCJ double copy. And we've been calling these relationships like Kerr-Schill double copy, Wahl double copy. There's been new advances in using twistors and also formulations in terms of convolutions. But unfortunately, in some cases, there hasn't been a direct connection with the amplitudes double copy. And that's what we're going to address in this talk. I'm going to try to show you how to get the classical double copies from the classical limit of the BCJ double copy using the K-Mock formalism. So in order to do that, we will start by looking at the very humble 3-point amplitude in electromagnetism of a scalar particle emitting a photon. And we'll show that that is actually enough to compute the classical field emitted by a static particle. Then we'll use this amplitude and this double copy map I'll propose, which is just the product of two 3-point amplitudes, which also takes into account all helicities. So we're going to be sourcing not just the graviton, but also dilaton and B field. And then we'll compute a curvature using these amplitudes as well. However, in this case, the curvature that we're going to compute, as we will argue, is not just the Riemannian curvature, the usual Riemann tensor, but a generalization of it that also includes dilaton and axion, which is this. And then finally, we'll look at classical double copies between the classical fields that we obtain from the amplitudes. And we'll recognize here some of the double copy prescriptions that are already known in the literature. And in this sense, we are going to show how the classical double copy emerges as the classical limit of the double copy for amplitudes. So let's start by looking at how to recover the classical field generated by a point particle using 3-point amplitudes. To set the stage, we are going to consider the state psi, which is a static wave packet of a massive scalar field, defined like this, where d phi is going to denote on-shell momentum integrals. And var phi is just the usual waveform of the wave packet, which we take to be sharply peaked around the classical momentum u, where u is a unit time-like vector. And we also require this ordering of the scales in order to have a well-defined classical limit, so that this corresponds to a particle in the classical limit. We're going to couple this state to a gauge potential, to a gauge field, which we're going to take as simply like U1, or you can think of it as Yang-Mills as well, but just a linearized level. And then our goal is to compute the classical expectation value of the field strength tensor. Now this computation, as we'll see, is actually rather easy because the final state is psi is actually coherent state in the photon. So the calculation simplifies massively. And that's what I'm going to show in the next slide. So here you have the same final state, psi, which I've written in terms of sums over amplitudes. These amplitudes, I've written them here. They have two external scalar lines, right? And you can have as many photons emitted as you want. So you have to sum over multiplicities. Now, this in general, this amplitude is of course complicated, but we are only interested in the classical limit of it. So we're going to use the K-Mock formalism. K-Mock stands for cos over maybe an O'Connell. And then you get a simplified version of this amplitude, which is just a sum over permutations of the half-ladder diagram. And moreover, this gets further simplified when you realize that the external photon legs have momenta proportional to h bar. So the internal propagators are to lead in order on shell as well. So if you work things out, or you realize that you can write this thing as the product of n copies of the 3-point amplitude, together with some delta functions. In this trick allows us to rewrite the initial final state that we had at the top of the slide as an exponential. So we see that we get an exponentiation of the 3-point amplitude, which denotes a coherent state, which simplifies the calculation of expectation values massively, because now every time that we have annihilation operator acting on the final state, that is essentially just bringing down a factor of the delta function with the 3-point amplitude. Now let's put this into practice by computing the expectation value, the classical expectation value of the field strength. I have written here the equation that we want to compute, and you can recognize here the combination that we've just talked about. And so what you get is just a factor of the amplitude with the delta function. However, now we have to step back and look at this expression, because we got something that is integrated over on-shell momentum space, and we have also delta function of k dot u, which is, I'll remind you that u is a time-like vector. So in real kinematics in Lorentzian signature, this integral has no support. You will get just 0. This is of course related to the fact that the 3-point amplitude in Lorentzian signature real kinematics vanishes kinematically. So you can do two things. You can either integrate over complex momenta in Lorentzian signature, or you can integrate over real momenta in split signature. That's a 2,2 signature. We've chosen the second option, basically because the integrals are a bit easier, and you get also real spinors. In 2,2 signature, all the spinors are real. But let me emphasize the fact that you could also do it in complex momenta in Lorentzian signature, and you can actually rotate back from one to the other if you want. So now let me note another thing, and is that in this language, using these amplitudes, the most natural objects to compute are not field strength tensors, but Maxwell Spinners, which are the result of heating the field strength with sigma matrices. If you compute the expectation value of these spinors, you get what is printed in this slide. And the important thing to note is that the Maxwell spinor and the dual Maxwell spinor are related to the positive and negative helicity amplitudes respectively. So you have this very clear relation between the spinors and the 3-point amplitudes. It is true that I haven't told you exactly what the 3-point amplitude is, and I've just told you that it's like a massive scalar line emitting a photon. That is right. If you take that simple amplitude, which is printed here, you essentially get a Coulomb particle, a point particle in electromagnetism. However, with a little bit of effort, you can do a Newman-Janius shift in this amplitude, and you get square root of Kerr, which is a solution in electromagnetism, which has extended source and some spin. In terms of spinors, this Newman-Janius shift accounts for a shift, a real shift in the Maxwell spinor, and the inverse shift or translation in the dual Maxwell spinor. Similarly, you can perform another transformation, namely electromagnetic duality rotation, to go from Coulomb to a dion. In terms of amplitudes, that corresponds to putting this extra factor e to the helicity theta. And again, in terms of spinors, this has a very nice interpretation, just as a product acting, well, multiplying the spinor, and the inverse factor multiplying the dual spinor. Of course, you can do these two transformations at the same time to get something like a spinning diamond. And let me also mention that this web of classical solutions in electromagnetism and also their relation to the double copy have been explored in these 3 papers that I'm listing here. But okay, so now we've learned how to extract classical fields in electromagnetism from amplitudes, from 3-point amplitudes. Now we want to take those 3-point amplitudes and compute the double copy to compute the relevance of the analogous objects in gravity. The double copy map that I'm going to use is this. This is just the product of the left and right 3-point amplitudes with some multiplicative factors in front. Again, we are going to use all the helicities. So we're going to map the plus helicity amplitude to the positive helicity graviton, minus to the minus helicity graviton, and then plus minus and minus plus are going to be a combination of dilaton and axion. However, now we run into a problem because we want to compute, as we did in electromagnetism, a curvature that is related to these amplitudes. But the obvious candidate, which would be just the usual Riemann tensor, would only depend on the graviton at linearized level. So we would be missing out on the plus minus and minus plus helicities. So in order to solve this, we're going to use a generalized curvature tensor, which also includes dilaton and axion. To do that, I'm going to do it in the in the context of Riemann-Cartan geometry, which is a generalization of Riemannian geometry in which you allow your connection to have torsion while you keep it metric compatible. So you have a connection like this, where this first term corresponds to the Levi-Civita connection, and the second term corresponds to something called contortion. And this tensor has to be antisymmetric in the first and last indices. If you do this, then you're going to have a metric compatible connection. Now we can populate these new contortion degrees of freedom with the B field and the dilaton in this way. This is motivated by the fact that when you compute the associated Ricci scalar of this connection, you get this, which it so happens to be up to this boundary term equal to the NSNS Lagrangian density. So you see that these things are equal up to this boundary term. So you can write the action just in this very compact manner. And this idea of packaging the B field and the dilaton into a generalized connection such that you get a nice action dates back to the early days of the NSNS Lagrangian. So notice, for example, this paper, this was one of the very first papers on NSNS by Sherk and Schwartz in '74. And after that, it was used to try to find higher order terms in the closed-in amplitude action in terms of just pure geometric quantities. And also I'm listing here this paper by Saar because he also used some metric compatible connection in that context. But okay, at the end of the day, what we really care about for our purposes is the linearized Riemann tensor, which takes that simple form. Let me now bring back the helicity state map that I mentioned before by mapping the annihilation operators of plus to the graviton ones and the mixed ones to dilaton and B field. And if you plug this back into the Riemann operator, you find this expression. And now we have something in which we can use the exponentiation that we discussed in electromagnetism as well. Because it also holds here, like before we did it for electromagnetism, but in gravity it's essentially the same calculation. So you can replace the annihilation operators by amplitudes and you get this, this. And this is a very compact and neat formula because I've written below the expression that we got a couple of slides ago for the field stress tensor. And you can immediately see that indeed this object is the double copy of this other object. Like, this is very evident if you look at the terms in square brackets. But okay, again, as we did for the gauge field, maybe the most natural object to study using this formalism is not the tensor, but the spinors. So I'm writing here the spinorial decomposition of this generalized curvature. And if you compute the expectation values of these spinors, you find the same thing. Namely, you find that each spinorial component is related to a helicity. In particular, the first two are at linearized level as equivalent to the Weyl spinors, which of course are related to the graviton degrees of freedom. And the second two are related to the dilaton and the axion. So now let's look at the more concrete example in which I'm going to consider the double copy of these two amplitudes, the left and right amplitude. We take them to be the most general ones that we've discussed here so far. So we put the duality angle and the spin parameter in both of them. Now, importantly, these parameters can be different for the left and right copies. So we are going to get an asymmetric double copy. If we run the double copy map, we compute the expectation values of the spinors with these definitions for the parameters, we get this result. Essentially, we get that the spinors with the deformation parameters are related to the spinors of the J and W solution. Now we already knew that the J and W solution, which is essentially a Schwarzschild metric with some dilaton in it, is the double copy of Coulomb. So we set all the deformation parameters to 0, we get J and W. Instead, if we have the deformation parameters, they basically induce certain transformations. And we can identify what those transformations are. Basically, theta bar, which is the sum of theta L and theta R, induces duality rotation in the Weyl spinor. That's an Ehlers transformation, essentially, which rotates Schwarzschild to tau naught. Delta theta, which is the difference in the two duality angles, induces a rotation of the dilaton and the axion. Now, this is a part of the SL2R group of the NSNS action. So it's kind of nice to see it popping out here. A bar, again, the sum of the spin parameters of the left and right copies, produces a Newman-Janer shift in the metric. And delta A produces a kind of mysterious shift of the dilaton and axion. We can look at this in terms of tensors also if you want, although it looks a bit more messy. And you get this if you set the spin parameters to 0 for simplicity. So this is the Weyl tensor that you get, and is rotation of the Schwarzschild Weyl tensor and the dual Schwarzschild Weyl tensor. So essentially conclude the same thing, that the theta bar is an Ehlers rotation. And similarly, for the delta theta, we get that it's a rotation between the dilaton and axion. Of course, we're getting hyperbolic trigonometric functions because we're in 2,2 signature, but that's completely fine. One last thing, and perhaps this is one of the most important conclusions, which is that we've described how to compute classical fields from 3-point amplitudes. And those classical fields satisfy some double copy relations. Now we want to identify those classical double copy relations as the already known double copy prescriptions. In order to do that, we are going to set all the deformation parameters to 0, just for simplicity. In the paper, we do it more generally, but here we're going to keep it simple. And we're going to look at the different terms appearing in the Riemann tensor independently. The last term is immediately 0 because we have delta 0 equal to 0. So we have no mixing of dilaton and axion. But the first term is probably the most interesting one. If you do a bit of algebra, you can actually show that the expectation value of that term can be written as the convolution of two copies of a field strength tensor with the inverse scalar potential. Now this, well, and also we have this P here, which is a projection, which deletes or removes all the traces. This expression is very reminiscent of the convolution double copy introduced in 2014 by Anastasio, Bornstein, Duff, Hughes, and Nagy. Moreover, we can take this one step further by using some of the properties of the scalar potential and realizing that this convolution can be turned into a normal product in position space. This equation now is basically the Val double copy written in terms of tensors. The Val double copy was introduced in 2018 by Andres, Ricardo Monteiro, Isabel Nicholson, and Donald. And so essentially, we've gotten the Val double copy from the double copy of 3-point amplitudes. So now we can ask what happens with the second term. Can you do something similar for the dilaton term? And it turns out that you can't. You can describe it in terms of convolutions, but since you don't have this projection operator acting on the whole thing, you cannot write it in terms of normal products. So there's something very special about the graviton degrees of freedom here, and for certain solutions in which you can do this. And with that, I'm going to just give you a brief summary of what we've done. We've obtained classical curvatures on fields from 3-point amplitudes, namely the Kerr-Tabnap family, which is something that was also done in a paper, well, 2 papers last week by Crowley, Guevara, Miller, and Strominger, and also Guevara. They also did it in split signature, and they also have a brief discussion in like 3-point amplitudes in that context. We also introduced a generalized curvature, which includes dilaton and axion. And we've seen how the Val double copy emerges from amplitudes in this context. There are a couple of things that we could do from here. For example, it might be interesting to try to generalize this to other theories or get more general solutions. In the paper, we also looked at heterotic gravity. And it'd be interesting to explore these spinning axi-dilaton solutions that we got, and because there are not many known in the literature. It'd be also probably quite good to look at this geometric meaning of the dilaton and the B field, see if there is any actual significance in that. And of course, the best thing would be to extend this to higher orders in perturbation theory, although this might imply that we have to understand a bit more of the role of gauge choices and the Kerr-Schildt simplifications in all this formulation. And that's all I wanted to say. Thank you very much, and I'd be very happy to take any questions.
Any questions for Dimitrios?
So suppose I start from a 3-point amplitude and obtain a classical field strength. Is it guaranteed that that field strength will obey Maxwell's equation, so that it is an actual solution?
Yeah. So I think as long as the amplitude is on shell, you probably get that from the K-Mock formalism. Although we've basically looked at very like at the amplitudes I've talked about. So if you consider something more complicated or strange, yeah, I respect that, yes.
And the same with gravity, I guess.
Yes, well, and again, we're doing things at linearized levels here, right? So in that sense, it's not very complicated to get something that is on shelf. Basically, you need box H to be 0.
Okay, Ira? Could you, in the last or second to last slide, could you explain where the gauge dependence sneaks in?
You mean here? Oops, here.
Yes. So can you point to the gauge dependent part?
So, well, this is not really gauge dependent in the sense that this is in terms of curvatures, right, which are gauge independent.
Right, but I mean, clearly in X space, you made a choice of coordinates, right?
Well, yes, we are using here like essentially we are perturbing around Minkowski signatures, so it would be Cartesian coordinates, although that's probably not necessary. The important thing here for this to be satisfied is that this S, the scalar potentials, has to satisfy an equation. Essentially, it means that the double derivative of this acting up, well, when you act on with the projection operator on the second derivative of S, it has to factorize into 2 single derivatives. So that way you get rid of all the terms and you get a factorized expression. So the magic here is not so related to coordinates, but to the specific solutions that you're dealing with. I don't know if that answers the question.
No, so let me ask, sorry, so let me simplify. Suppose you wanted to get the Kerr shield form, right? So in other words, the next step you wanted to take, say, is to calculate the metric, right?
Yeah.
So at some point you're going to have to choose a gauge, right?
Yeah, if you want to compute the metric, you have to compute it. You have to choose a gauge. Yes.
Yeah. So I mean, but isn't that your eventual goal, is to get the solution? Sorry.
Well, you can do that by from the Weyl tensor, right? If you impose, like, say, the Donder gauge, you can basically get the metric from there. The thing is, maybe something related is the problem that Kerr shield is not actually like a normal gauge.
Right.
It's just a family of metrics. So,
yeah,
more questions?
maybe I could say something. Well, if Julio let me. Yeah, I mean, so the Weyl spinner, these curvatures characterize the space-time. Once you've got those, you can compute the metric if you want. You'll have to introduce a gauge to it.
Right.
But at least in linearized theory, this thing is gauge invariant, so
right,
you don't need a gauge. Perfectly on shell.
Right, but I guess I guess my question is, what's the eventual, like, what's the end goal?
Well, I mean, the end goal is just to understand that the Schwarzschild really is a double copy of Coulomb. This makes it clear.
Okay, not
this is the end goal.
Necessarily to try to find other double copies.
I mean, I'm going to say a little bit more about this when I speak, but I don't know if you're going to hear it. But
well,
yeah, I mean,
wait then.
Okay, there's a question on Zoom. Speak up.
Hello, do you hear me?
Yeah.
So what do you mean by higher orders in this context? Is it adding more, like multiplying more 3-point amplitudes, or adding loops in these amplitudes that you multiply?
So I'm referring here, we are computing the expectation value of this object, right? Like the linearized Riemann tensor. Of course, you can have higher orders of in the coupling here, right? Like terms with h squared or combinations of the dilaton and B field. So that's why I'm referring to like high orders in the coupling. Of course, when you compute those, you might get more complicated things, like loops might start appearing and all that.
Okay, thanks.
All right, so I think with this, if there are no more questions, we can thank the speaker again.